So we're recording live now. This quarter, we're going to start with finishing up some of the material that typically gets done in a fall quarter, but things were just more cumbersome fall quarter. But we'll start with chapters 9 and 10, which have to do with rotation and rotational motion. And then actually we'll be doing those this week. And so the rotational motion stuff, some of it's very closely related to things that we did fall quarter. It's just looking at rotations instead of linear motion. So we'll have that. And that'll be this week, chapters 9 and 10. And then next week, we'll have take a look at chapter 13, which is gravitation, and do a few things with that. And then we'll actually have our first test. This quarter, we don't have a final test. The different subjects that we study this quarter are kind of unrelated in a way, and so it doesn't really make sense to try to tie them together into a final test. So at the tail end of the quarter, all we'll have is just a last unit test. But anyway, the first unit test will be next Thursday or Friday. I'll try to set it up so that you could probably take that on either day. We'll probably have a review for that test. I'm not sure just when, but anyway, I'll probably schedule the test reviews outside of regular class time, and I'll do a survey to figure out when good times for office hours are, and so we can have office hours like that. Our second unit is going to be on oscillatory motion, mechanical waves, and sound. And so that's something that'll be completely new for us. And then our third unit is going to be on optics. We're actually going to hop way forward in the book to a couple of chapters on optics. I don't know if it's 2 or more. One part of it is going to be on what's called geometrical optics, which is ignoring the wave nature of light for the most part in the geometric optics. And you just look at lenses and mirrors and image forming and things like that. And then the second half of the optics unit is what's called physical optics. And for that, we do take into account the wave nature of the light. And so we'll start thinking about, it'll be related in that sense to the second unit, where we'll have waves in there, but some fairly challenging things in the latter half of the optics unit. And then the last unit, if we manage to squeeze it in okay, is just a brief introduction into thermodynamics. And those of you who've taken a chemistry class, some of the ideas are going to be very familiar to you. We tend to do things a little bit differently in physics when it comes to thermodynamics. And so just a little bit different. Thermodynamics is an area where some of the subjects in there, I don't know, they were very bizarre. We actually don't get to some of those more bizarre topics. When I took this class at Eastern, it was actually spread out over 5 quarters. And so we got to do almost every chapter in the book over those 5 quarters, although things were different. The first 2 quarters, we were doing epsilon delta proofs and things that we were doing in calculus. And I don't know why we were bothering to do them in a physics class, but we were. And we had very thorough introductions into integration and differentiation in the physics class. And it was nice having that. It reinforced what I was taking in calculus at the same time, but we don't do that here. We don't have 5 quarters to spread it out over. But anyway, that's where we'll start from. And chapter 9, the one we're starting with, has to do with rotational motion. Oh, one thing, homework is going to be different this quarter. I realized grading the third test and the final test that a significant chunk of the class was apparently not doing much at all in the way of solving problems, where I'd ask a question and there would just be no familiarity with the topic. And so the homework assignments will still have the 4 conceptual questions a week typically, but the problems I'm going to have you turn in, instead of turning in a super detailed problem solution for solving the problem, I'm going to have you do just a more typical problem solution, although it will start with a given and to be determined. I want to reinforce that behavior. It's something that the engineers expect in their classes, and many of you are going into engineering, and it's just a good way to summarize the useful information. But then as far as working through it, I'm not going to require the sentences of explanation throughout the thing and that sort of stuff. So pretty much just the math, although I do expect you to start with, in every case, a formula in variable form that's a basic formula from the book, and then introducing, what are the knowns that you have in the problem, and just working through the solution. And I'm wrestling with the idea of whether or not I should have you do a reflection paragraph at the tail end. It's very valuable for you to do that, but I'm going to have 10 or 12 problems on each assignment. Not all of them are going to be super hard. Some of them will be pretty much straightforward, but it'll be a size more like the assignments that I had when I was taking this class. And anyway, more problems to turn in, more PDFs. A couple things that I've got to get people going on is learn how to turn in a multi-page PDF, because I was getting tests and homework assignments that were, instead of PDFs, they were JPEGs, and I have no software where I can edit a JPEG and put comments into it or anything like that. And so if I get a JPEG for an assignment or a test, it's not getting touched. I'm just not going to do anything with it. So be a little bit more strict in that regard. Anyway, let's dive into chapter 9, having to do with rotations. And so I'll switch the view here and we'll go over to the visualizer. And you should be seeing a pen on a white sheet of paper right now. So a couple of key ideas that you're going to need for this are being familiar with Radian Measure again. And so for Radian Measure, here's the center of the circle. I don't know if you can see that dot there very well, but there's our center. And there's a radius. And here's R. This is an angle theta. And here's an arc length S. And for Radian Measure, the angle theta is defined to be, whoops, that's not a very good theta, but it's just the arc length divided by the radius. And there's this relation that exists that if you go all the way around a circle, the arc length you get happens to be 2 pi times the radius. That full circle, the angle would be 2 pi. But there's our definition of Radian Measure. We're going to use this. It pops up, a few times. It pops up in optics, actually. We'll be using something called the small angle approximation when we get to optics. And it turns out that when the angle is very small, there isn't any difference or any worthwhile difference between the angle theta and the sine of theta and the tangent of theta. So we'll use that approximation a little bit later. But for now, we'll just go with what we have here, that S over R is just going to be the angle theta. Now, we're going to think about rolling motion, or that kind of rotational motion. Well, actually, let's just imagine a round thing that's spinning. That would be easier. We'll get to rolling motion pretty soon. And so I'll just have some round thing here that is spinning. And here's the center of it again. And doesn't matter which way it happens to be spinning. I'll just draw an arrow that indicates that it's rotating in the clockwise direction. So we've got that. And this thing will have some radius r. Now, we'll imagine for starters that it's spinning at some uniform rate. And we're going to talk about how fast it's spinning. Well, in common usage, one of the ways that people measure the speed at which something is spinning is RPM, and that stands for revolutions per minute. I've got routers that some of them have adjustable speed on them. I've got a router that spins at somewhere larger than 20,000 revolutions per minute. That's pretty fast. It's something you definitely want to be wearing hearing protection for when something's going that fast when it bites into a piece of wood, because it's very loud with a bit. But that's a common way of measuring how fast something is speeding or turning. You've got revolutions on top. That's actually a measure of the angle that it's turned through, at least if you take those revolutions and multiply each one by 2 pi for the radians, or 360 degrees for the radians. But we'll typically use radian measure in this unit and not mess with degrees on this. So it probably won't matter whether you've got your calculator in degrees or radians, because the equations that we're going to develop are going to work pretty much okay. You won't be taking the inverse sine or the sine of any of these angles or anything like that. But revolutions per minute is one way of measuring this quantity we're going to be interested in. And we'll call that angular velocity. Now, when we call something a velocity, that's a vector quantity. It has a direction. Well, for what we're going to do with giving it the direction, we'll just say we'll look at it from so that we're looking down at this round object and we see it turning, and it'll either be going clockwise or counterclockwise. But there are ways of defining a direction to an angular velocity that isn't just clockwise or counterclockwise. And I'll introduce that idea. In that case, if something was going in this direction, where it's rotating clockwise, we'd assign the vector for the angular velocity to be into the page. And we use something called a right-hand rule for that. Similar to a right-hand rule, let's see, Nolan, I think you took linear algebra. I don't know. I doubt if anyone else has. But we'll be using right-hand rules quite a bit. And the way you use a right-hand rule in this sense for this rotation is you curl the fingers of your right hand in the direction the thing is turning, and your thumb will point in the direction of the arrow for the angular velocity. Now, we're not going to have to worry about that right off the bat until the next chapter, but that's something that's kind of interesting about that. Well, we're not going to be using revolutions per minute for the most part, but once in a while we'll hop back and forth between that. Instead, we're going to want our angular velocity to be in radians per second. And if I look at what I've got here, this theta equals s over r, if I take the time derivative of theta, with respect, well, the time derivative is the derivative of theta with respect to t. That will be our angular velocity. And sometimes it'll be constant, so I could just as well use a delta theta delta t. But sometimes it'll be speeding up or slowing down, in which case there's actually going to be some angular acceleration. But this will be our definition for angular velocity. The change in the angle, you could imagine an object starts here and ends up here, traveling along this circular path. It'll be the change in the angle divided by how long it takes to do that. And we're going to use a new Greek letter for us, which is the Greek letter omega. And don't confuse that with W, which looks like this. So don't get these two mixed up with each other. So anyway, that's a joke because I tend to make them identically. So although sometimes I'll try to make my W's look like that. But anyway, that's the Greek letter omega. And that's the symbol that we'll use for angular velocity. Now, we will be able to develop parallels to our linear equation motions. And here's what some of them are going to look like. And I'm just going to make a little table here that'll show that. Don't need that long ruler. Start off with our constant velocity equations from, we'll have linear and rotational. Well, something we had linear-wise, we had that the speed was equal to dx dt. Okay, well, let's see, rotational-wise, we'll have angular velocity is going to be d theta dt. So that's a fairly straightforward thing. In linear motion, if we had constant, and I'm going to start with constant velocity here. Okay, constant velocities, an equation we had that was x was equal to x naught plus vt, and the v was constant. So there is an equation we had. Well, in rotational motion, instead of having x's, we're going to have thetas. And so we might say theta is going to equal theta naught, whatever its original measure was, plus omega t. Now, we could have signs for velocity. If something was going in what we chose as the positive direction, it would have a positive velocity. If it was going in the what we chose as the negative direction, we'd have a negative velocity. We can have the same thing with rotational motion. If something is turning in what we've chosen to be the positive direction, it has a positive velocity. If it's going the opposite direction, it has a negative velocity. So sometimes fall quarter, when we were assigning a direction to something, we would just write a positive sign with an arrow on top of it to indicate that positive was to the right. We can do the same thing with rotational motion. You just put a plus sign, and if you want positive to be the clockwise direction, you just make a little symbol like that. And that's a nice shorthand notation in your problem solutions to indicate what the positive direction is. A lot of times, though, we'll use the convention from mathematics that if you've got an XY plane here, if you, I don't know if you've gotten to polar coordinates or what quarter in calculus you do that, but you'll have the positive direction for rotation is counterclockwise. And so in that case, when you're solving a problem, you'd have to just have a little thing that looks like that. So that's how you could indicate positive in the other direction. So there's something that you can have with rotational motion. And as far as constant velocity goes, that's not so interesting. And we won't do much with those, but still you could think about it. You could imagine, actually, we could just make up a real quick problem for that. A saw blade. Let's see. Turns at 757 RPM. That's revolutions per minute. We'll ask a couple of questions. And we'll imagine that this is constant. So I'll say a constant 757 RPM. So a question, what is its angular velocity in radians per second? That's just going to be a unit conversion here, so that's not that big a deal. But also, or through what angle does it turn in 35.0 seconds? Well, once you figure out the angular velocity in radians per second, that'll be pretty easy to figure out. So let's see, angular velocity in radians per second. Well, you know that its angular velocity, 757 RPM, is an angular velocity. That's 757 revolutions per minute. It's just that it's not that easy to figure out some of the things that we're going to want to know in terms of these other things. Okay, well, let's see. So I multiply that by, in 1 minute, there are 60 seconds, and I'm going to want seconds on the bottom when I get done here. So I'll put the 1 minute on top and divide by 60 seconds. This is an exact conversion, so I don't need to worry about sig figs on something like this. And then I also have to take into account that there are 2 pi radians in every revolution. And so I would just put 2 pi over 1 revolution. So things that'll divide out, the revolutions will divide out, the minutes will divide out. And it's understood that anytime you've got a pi sitting there, you're talking about radians. You don't even need to write it in. In fact, radians, the radian measure is a ratio of length divided by length. So it's actually a dimensionless quantity. It's like a placeholder word that we put on things. Same with a degree. It's a pretty weird quantity. But anyway, that's the way that you would convert from revolutions per minute into radians per second. And it's easy enough to do that. And I get about 79.3 radians per second. So that's the first part there, angular velocity in radians per second. Then through what angle does it turn in 35.0 seconds? Well, theta is going to equal theta naught plus omega t when it's got a constant rotation or angular velocity. I could just think of delta theta equaling theta minus theta naught, and it's just going to be omega t. And you would just take this thing and multiply it by the 35.0 seconds. And I'm not going to bother to plug in the numbers here, but that's how something would show up. Now, a point that's on the outer rim of this thing is going to travel a distance s in a particular time. And when I introduced the idea of angular velocity, I did d theta dt just equaling what the angular velocity is. But because theta is going to equal this quantity, I can actually take a derivative of this thing as well. So my omega, which is d theta dt, is going to equal ds dt times 1 over r. Okay, the 1 over r is a constant. I could stick it in front. ds dt is going to be the tangential velocity of whatever it is that's moving along the surface of here, or a point on the rim of this thing. And we usually don't bother calling it tangential velocity. It's constantly changing direction, for one thing. Tangential speed might be better, but we'll just stick a v on that, and we'll get v over r. And so omega is going to equal v over r. Now, that speed is going to depend on how far out the thing happens to be. If we pick a spot that's not so far out, like say here, it'll turn through the same angle in an amount of time, but it's not going as fast. And as you get closer and closer to the inside of the thing, actually, if you solve for v equals r omega, you can see this better. Everything on a turning solid object is going to have the same value for the angular velocity, but its linear speed is proportional to the radius. So something that's at the center doesn't go anywhere. All it does is turn. Something that's a smidgen out from the center isn't going very fast in a given time delta t. That's all the farther it goes. But the farther out something is, the faster it goes. And so there's something. But this is a nice link between linear and rotational motion, is that v equals r omega. Here's someplace that may show up. Remember tangential acceleration? It was equal to v squared over r. Well, with v equaling r omega, that would be r omega squared over r, which ends up being r squared omega squared over r, which is equal to r omega squared. There was a few times last quarter, I think maybe on the formula sheet, I might have had this formula on there, and I saw some people attempting to use this equation on a test when they had no idea what omega stood for. And don't do that. But after this, you'll be able to do that. You'll know what omega means. And so you could figure out something like that. Okay. We have that going on. Well, let's go back to adding to these things. Let's write our constant acceleration equations here. So okay. Well, in that case, let's see, we'll have some basic definitions. We'll still have v is dx dt, but it's not necessarily constant. So omega can still equal d theta dt, but it'll be something that's constantly changing. We can have acceleration equals d squared x dt squared. Okay. Well, what's that going to look like for angles? That will be, oh, it can also be dv dt. For angle, that'll give us an idea of an angular acceleration that could be d omega dt. Okay, I replaced v with omega to talk about rotations, and that'll equal the second derivative, d squared theta dt squared. And this will be angular acceleration. Now, for angular acceleration, we use the Greek letter alpha, and that's my version of alpha. Let's see, you can get as fancy with it as you want to, but that's good enough for me. That's our symbol for angular acceleration. Okay, well, in linear motion, when we had acceleration, one equation we had was v is equal to v naught plus at. Okay. We can have an analogy to that in rotational motion, or an analogous equation, where we'll have omega is going to equal omega naught, the angular velocity at time 0, plus alpha t. And so that's going to look an awful lot like what we had over here. And then we had an equation that looked like x was equal to x naught plus v naught t plus 1/2 at squared. Turns out for rotational motion, we change the x's to thetas, we change the v's to omega, and we change the a to alpha, and it works just fine. And so we'll have theta is going to be theta naught plus omega naught t plus 1/2 alpha t squared. And as long as you keep track of your units carefully, things will be just fine solving your way down here. Just remember, let's see, theta is in radians, omega is radians per second, and alpha is going to be actually radians per second squared, d squared theta dt squared. The dt will be in seconds, square it and you get seconds squared. Theta is just going to be in radians. So that's what we will have for those equations. Let's see. Other stuff, there was a v squared equals v naught squared plus 2a delta x. I remember right. You had to be real careful with signs on this one. But here, we could rewrite that as, instead of v, we have omega. Omega squared equals omega naught squared plus 2 times, instead of a, we'll have alpha. And instead of delta x, we'll have delta theta. So there, all kinds of things that can get linked together on these things. Now, the alpha was d squared theta dt squared. If we remember that theta is equal to the arc length divided by the radius, if I take a derivative of both sides of this, the radius, we're going to assume that we're dealing with a point on whatever is turning that's always the same distance away from the center. We're measuring its distance out from the axle. And so take a time derivative of that. We did this once. d theta dt is going to equal 1 over r ds dt, which is 1 over r times v. That's the speed of that point out there. Take a second derivative. So d squared theta dt squared would be to take the time derivative of 1 over r times v, and the 1 over r is a constant. It can come outside the derivative, and we'll have 1 over r dv dt. Now, this is the time rate of increase of the speed of the object. When we were looking at circular motion, we called that the tangential acceleration. And so, and as long as, well, we'll just call that the tangential acceleration. But this d squared theta dt squared is what we called angular acceleration. Turns out the angular acceleration is 1 over r times the tangential acceleration, or the tangential acceleration is r times alpha, the angular acceleration. We also had that that other link somewhere here. I don't know where I wrote. Here it is. V is r omega. So these are things that tie these together. And sometimes these will be handy relations to be able to use. And we could also say that S is equal to r theta as well. So working from this one up, all you do to get to the other ones, I mean, you start with the definition of radian measure, take the time derivative of both sides, and you get to this. Take the time derivative of both sides, and you get to this. You do have to recognize that the acceleration that you get by taking the derivative of the speed with respect to time doesn't include the radial acceleration. It's just going to give you the tangential acceleration. You could get it to, it's kind of beyond the scope of our class, but in a more advanced, let's see, dynamics class. In physics, we call the more advanced class classical mechanics. In engineering, it would be engineering dynamics, but you may treat all of these as vector quantities and take derivatives. And when you take dv dt as a derivative, because it's also changing direction, you can get both the tangential and the radial acceleration out of that. But that's more complicated than we want to go with. So there's something that we have there. Okay. Other parallels you might have. This is just for the describing the motion stuff. And I'll find some example problems to do with this. But other things that can be parallel, another one that we'll look at is energy. And energy is where something gets very interesting. What did I do with that other ruler? There it is. Okay, we'll just imagine the energy of some object. It could be any kind of thing. And look at what that might happen to be. And for the energy, we've got kinetic energy is equal to 1/2 mv squared. Okay, 1/2 its mass times its speed squared. No direction to this. Energy, kinetic energy is a scalar quantity, so it doesn't matter what direction the thing happens to be moving. All that matters is the speed at which it's moving. Now, let's imagine a round object that's turning, and I'm just doing it with round objects because they're easier to draw with a compass. And but it doesn't necessarily have to be round. It could be any kind of shape you want. So here's our round object. There's the center of it. And we'll imagine that this thing is turning, and let's just make it turn in the, I have a dying pin, I think. Imagine that we have an object turning in the counterclockwise direction. Okay, where did I stick my other pin? So it's going to have some, at some instant, and doesn't matter for this consideration whether it's a constant angular velocity or it's accelerating or anything. We're just interested in the energy at some instant. Okay, well, if it's turning with an angular velocity omega, some parts of it are going to be going faster than others. The little chunk right here at the center, is barely moving at all. Remember, the speed at which something is turning is r times omega. And if r is tiny, like for something right near the center, it's not going to be going very fast. And so it won't have much kinetic energy. But if something is all the way out here, the distance r away from the center, the things out here are going to have more kinetic energy than the things in close to the center. If I want the kinetic energy of the object as a whole, I'm going to have to take into account all those varying speeds that are out there. Now, to do this right, you'd have to use the idea of integration that comes from calculus. And some of you are just starting second quarter calculus, so you probably haven't done integration yet. But we can imagine doing a sum. And the kinetic energy of the whole thing would equal a sum. And that's what that Greek letter sigma stands for. And we'll just imagine dividing this thing up into a whole bunch of little tiny chunks, each of which is going to have a distance r sub I away from the center of the thing, and a little mass m sub I. Okay, and so this will be one little chunk of mass, this will be another chunk of mass, another one here, all with their own radii away from there. And to figure out the kinetic energy of the whole thing, we'll have to add together. And so we'll sum for I equal 1 to some lowercase n, where n is some really big number, because we want to split this into a whole bunch of tiny chunks. And then for every one of those little chunks, we'll take 1/2 the sum of the m sub I times the v sub I squareds. Okay, so we'll have to go to all that trouble and try to figure this thing out. Well, remember, the v sub i's are going to equal r omega, but r is something that depends on which I we happen to be dealing with. But I can rewrite this as 1/2 the m sub I times the r sub I squared omega squared. When you square r omega, you'll get r squared omega squared. So that's what we have. Now, this is a sum. Think about what this means. It would mean the kinetic energy is going to equal 1/2 times m1 r1 squared omega squared plus 1/2 m2. Maybe this is object 1 here, this is object 2, this is number 3, this is number 4. And so m2 r2 squared omega squared. They've all got the same omega, plus dot 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 plus 1/2 m sub n r sub n squared omega squared. So you're going to have n terms in this sum, where n is a really big number. But every one of those terms has a 1/2 in it, and it has an omega in it. And so you could rewrite this as 1/2 times, I'm going to take m1 r1 squared plus m2 r2 squared plus dot 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 plus mn rn squared times omega squared. And I could have just pulled the omega out and stuck it in front, but I wanted to keep it here so it looks like that. Now what I've got inside here is a sum from I equal 1 to n of m sub I r sub I squareds. And so this kinetic energy ends up looking like this. 1/2 the sum of m sub I r sub I squared, and I can wrap that in parentheses if I want to, times omega squared. this is analogous to 1/2 mv squared, but this thing in the parentheses here is a rotational analog to translational mass. Okay. In the kinetic energy, we've thought of mass as a measure of how difficult it is to accelerate something. Okay. We'll think of this as a measure of how difficult it is to make something rotate, to make its velocity, angular velocity, change. Okay. And we call this thing rotational inertia. Is that still showing? Nope. And I don't know why in physics we use the letter I to stand for rotational inertia. And so we'll have the kinetic energy is going to equal 1/2 I omega squared. Okay. I have to run out to school right after our class today, but while I'm there, I think I'll set up a demonstration that I can show you a couple pictures of. Maybe I'll even manage to take a video of it. I'm not sure. But anyway, I wanted to show you something that's going to happen with that. But anyway, we'll have this definition that the rotational inertia is going to be a sum of I equal 1 to a whole bunch of different things of the m sub I, r sub I squareds, and that r is going to be the different distance away from the axis of rotation. So we'll have to take that into account. Now, a more formal definition of I for when you have a continuous mass distribution is going to look like this. It's the integral over the mass of r squared dm. And if you've had second quarter calculus, you can recognize what this thing is. We don't tend to do a lot of integrals like this in calculus classes. They're usually more straightforward, although maybe with David Mayhew teaching the class, he's had a fair amount of physics. He just might introduce something like that later in the year. Although I don't know if David is the one teaching all the calculus this year or not. I haven't kept track. They may have 2 sections going. But anyway, there's our rotational analog for kinetic energy. Kinetic energy is 1/2 I omega squared. And when I record the video out at school today, I'll show you a setup I can do. I've got these platforms that I can attach masses to, and you can see different rotational inertias on the thing, and I can arrange a bunch of weights on those things in different places, and I'll show you one situation where the weights that I put on it are close to the center, and then another where I've got the exact same amount of weight on the thing, same amounts of mass on the things, but they're far away from the center, and it has a profound effect on the rotational inertia of the thing. And it's because the rotational inertia goes with the square of the distance away from the center. So making something twice as far away ends up making the rotational inertia 4 times as big. And that can be kind of interesting. Okay, this is just an introduction into the mathematics of rotations, and we'll have to look at the problems. But for today, you should be reading sections 9.1 through 9.3, and I'll post the homework later today, the homework assignment for week 1, and you should be able to do the first 2 problems in there after having read the book carefully and gone through this stuff and read the example problems in the book. And then tomorrow we'll move on from there. So, and I've got a lot of stuff that I have to stick up on the Canvas site for today. And part of it will be a a syllabus schedule for the first couple of weeks. And so tons of things to do. So does anyone have any questions on stuff that we looked at today? We're taking off just right from the word go. The tests this quarter, I don't know if we're going to have 4 or we might have 4 unit tests this quarter, but I tend to give them slightly different weights on the grade because we spend different amounts of time on there, but I don't know. I'll still have to think about that. I may actually come up with something creative, but we'll see what happens on that. Anyway, we got barely off the ground here today. We'll continue on with this stuff and tomorrow, and more to come. But be looking out for that first homework assignment and some guidelines on the homework solutions for later today. So watch for that, and I'll see you tomorrow.